Before we dive into today's episode, make sure to hit that subscribe button. It's the best way to stay updated with our latest insights.
Ladies and gentlemen, welcome to the CTSS Academy podcast. The energy is electric. The crowd is alive. Let's dive into greatness. We're champions strong.
Before we start the show, don't forget to check our new ebook, Kill All Bugs, Learn Software Testing in One Day. For a limited time, it's only $9.99. Links in description.
Welcome to the Deep Dive, the place where we don't just summarize sources. We really try to extract the core operational knowledge you need to be instantly well-informed.
Yep.
Today, we're diving into something that's, it's the absolute bedrock of critical thinking, of research, of data analysis.
It really is.
We're talking about the essential difference between dependent and independent variables.
And it is so fundamental, but it's one of those things that constantly gets wrapped up in, confusing jargon.
For sure.
The source material we're looking at today does a fantastic, clean breakdown. It really moves beyond just the textbook definitions and shows you how to practically use this distinction.
And that's the key, right?
That's what separates a student from a skilled analyst.
That's the mission right there. If you understand IVs and DVs, you understand the structure of pretty much any argument.
Any argument.
So we're going to unpack the clear definition. We'll explore the practical implications, like how researchers measure and control them. And then we're going to lock it all in.
Oh, yeah, there's a great mnemonic for this.
A great mnemonic and some really tangible, real-world examples. By the time we wrap up, you won't just know the definitions. You'll know how to spot the cause and the effect in, well, any scenario.
So let's just jump in. Let's set the stage for the relationship itself.
Okay, let's unpack this.
Yeah.
The entire purpose of this whole distinction is to define cause and effect. So let's start with the simplest definitions from the source.
Okay.
The independent variable, or IV, this is the variable that it stands alone. Its value never depends on any other variable in the study.
And if the 5V is the starting point, then the dependent variable, the DV, that has to be the endpoint.
Right.
Its value fundamentally depends on the independent variable. You can think of it like a domino effect. The IV is the finger that flicks that first domino.
That's a great analogy. So if we're trying to establish or test a causal relationship, which is, the goal of most research, the independent variable is always the presumed cause.
Always. It's the factor you're observing or testing or manipulating to see if it makes a difference.
And so if the IV is the presumed cause,
then the dependent variable has to be the presumed effect.
Simple as that.
It's the measurable outcome. It's what changes or doesn't change in response to that finger flick.
This brings us to a really crucial point about the directional relationship. It can feel obvious, but it gets muddled all the time.
All the time.
A change in the independent variable must affect the dependent variable for a relationship to even exist. But here's the key part. It has to be a one-way street.
A one-way street. I like that.
A change in the dependent variable can't, retroactively affect the independent variable.
Exactly. If we're looking at how revision time, that's the IV, affects your test score, the DV.
Okay.
The hours you spend revising cause the score to change. But the score itself doesn't jump back in time to change how much you revise.
Right. The direction of influence is fixed.
It's fixed.
That directional certainty is so fascinating because it forces researchers to approach these two variables in, totally different ways when they move from theory to actual measurement.
It absolutely does. And this brings us right into the practical differences that our source material highlights so well. That one-way direction is why the names actually change once you start running calculations.
I found this part so useful because in theory, we just say IV and DV. But in statistical modeling, especially if you're trying to predict something, the independent variables are often called predictors.
Or regressors.
Right, predictors or regressors.
The term predictor is pretty self-explanatory. You're using this variable to predict an outcome. But regressor, that's where the power lies.
Tell me more about that.
Well, when you have 5 or 6 potential causes, say age, income, education, all trying to explain one outcome, you're running what's called a regression analysis.
Okay.
You're literally trying to fit a mathematical line to the data to see which of those regressors, those variables, best explains the outcome.
So if the IVs are the predictors or regressors, the dependent variable just becomes
A predicted variable.
the predicted variable in those models. The terminology change really underscores their function. One is the input driving the equation, the other is the result you're solving for.
And that contrast leads to a huge difference in how we even get the data for each variable. The sources point out that independent variables are often surprisingly easy to get.
Right, they say they do not necessarily require complex mathematical procedures or observations.
They can be simple counts or, existing classifications.
Can you give us an example of that? Because when the sources mention complex mathematical procedures, what does that actually look like in practice?
Sure. Think about a study on, say, depression and exercise. The independent variable might be exercise time. You just measure it in minutes per day. It's a simple raw count.
Easy to observe?
Very easy. But the dependent variable is depression level. You can't just count depression. It's what we call a latent variable.
Latent variable, meaning it isn't directly observable. It exists, but you can only measure it indirectly.
Exactly. To measure that DV, the depression level, you have to use a standardized tool, like a clinically validated survey with maybe 20 questions.
Okay, I see where this is going.
And each answer gets a numerical weight. Then you add up those scores, you often run them through a formula to standardize them, and only then do you get a mathematically derived score, say from 0 to 50, that represents the dependent variable.
Ah, okay. So the IV is a direct measure. The DV is a complex derived one.
That's it.
That makes the difference between easily obtainable and requiring complex equations so much clearer. It's not about the algebra. It's about the difficulty of just quantifying the effect itself.
Precisely. And because the independent variable is the input, it's the one the researcher has to manage or even manipulate to test the relationship.
Right. The sources are really clear that IVs can be manipulated by the researcher, and this manipulation is the whole point of a controlled experiment.
And when we say manipulation, we should probably clarify that. It doesn't always mean artificially changing something. It just means controlling or observing the variation.
Right. So if you're testing a new drug, the manipulation is assigning different groups, a 10 milligram dose, a 50 milligram dose, or a placebo. That assignment is the manipulation of the IV, which is dosage.
Right. And for the experiment to be rigorous, to actually isolate the cause, the researcher has to control only the independent variable and keep everything else constant.
That's the cornerstone of the scientific method.
It is. And conversely, the dependent variable, the outcome, that cannot be manipulated by the researcher. You measure the result, you don't control it.
I mean, if you started manipulating the DV, like adjusting a student's test score to make your study look better,
well, you'd invalidate the entire thing.
you'd have junk data.
Yeah.
The DV has to be allowed to respond naturally to the input of the IV. You control the inputs, you measure the outputs.
That distinction is so key for rigor, and it flows perfectly into how we visualize the entire relationship.
Okay, and this is where it gets really interesting for me. If you're presenting data, you have to follow the convention for plotting these variables, and understanding why they go where they do is the ultimate memory aid.
It really is.
The independent variable is always positioned horizontally on a graph. That's the x-axis.
That horizontal x-axis represents the variable you're changing or observing. It's the time, the dosage, the hours spent studying. You move along that axis to see what happens.
Which means the dependent variable, the effect, is positioned vertically on the graph, the y-axis.
And the visualization is so powerful because as the IV on the x-axis changes, you measure how the outcome, the DV on the y-axis, responds by moving up or down. You are literally plotting the dependency.
And to help you lock this in for, a test or just a quick analysis, the sources provide one of the best mnemonics I've ever seen.
That's a classic. DRY mix.
DRY mix. If you can remember those 6 letters, you can label any graph instantly.
I think we should break down why it's so good. Let's start with DRY.
Okay, so DRY covers the outcome variable, the effect.
Right. The D is for dependent variable, the R is for responding variable, and the Y is for y-axis.
Dependent responding y-axis. It's what responds to the
Right.
change. So good. And then you have the cause, the input, which is covered by MX.
MIX.
The M stands for manipulated variable, which is the one we change. The I is for the independent variable, and the X is for the x-axis.
Manipulated independent x-axis. Using DRY mix is just a fantastic shortcut. It anchors the manipulated cause to the x-axis and the responding effect to the y-axis.
No confusion, guaranteed.
So with that framework in place, let's ground all this by applying it to the real-world scenarios in the source material. This is where it all becomes concrete for you.
Let's do it.
We can start with the educational one. It's usually the easiest to picture. So We have a teacher analyzing why some students score better than others on a science test.
Okay, and the test is scored from 0 to 100.
Right. She wants to predict that score based on two factors she thinks are the cause.
Okay, so the outcome she's measuring is the test mark. That mark is dependent on what the student did beforehand. So the test mark is our clear dependent variable.
And she suspects two causes. The first is revision time, measured in hours. The second is intelligence, which is measured using an IQ score. These are the input she's using.
So both revision time and IQ score are the independent variables. Exactly. They are the presumed causes.
Right.
And this example is great because it shows that complexity doesn't always come from a complex effect. Sometimes it's because you have multiple causes.
That's a great point. You can have 2, 3, maybe 20 independent variables all feeding into one single dependent variable.
For sure. The cause is often multivariate, but the effect is the singular outcome you're measuring.
Okay, let's switch gears to a business context, a classic one. How does an increment, a pay raise, affect employee motivation?
So if a company is running a study on this, the change they're testing is the raise itself. Therefore, the independent variable is the increment.
And the outcome they want to measure is the resulting employee's motivation. That's the dependent variable.
And remember our earlier point about complexity here? The increment is just a simple dollar amount. That's an easy IV to measure. But motivation, that requires a complex survey or some kind of index to generate that final numerical DV score.
It's another latent variable.
It is. And this distinction holds up even in broader economic contexts. The sources also gave that macro relationship between higher education and income.
Right. Intuitively, we all kind of feel that having a degree causes you to earn more.
Generally, yeah.
So getting that higher education, that's the cause, the input, the thing that happens before the outcome. So that's the independent variable.
And the measured result, the benefit you get from that investment, is the higher income. That's your dependent variable.
And if we were to graph that, we put years of education on the x-axis, the IV, and salary earned on the y-axis, the DV.
And you'd chart the dependency.
So just to recap, we've walked through the definitions, we've clarified that one-way directional relationship, we've highlighted the differences in measurement complexity.
How IVs can be simple inputs versus DVs as these complex derived indices.
And we've seen how a researcher controls the IV to measure the DV. And we capped it all off with that visualization tool, DRY mix.
So what does this all mean for you, the listener? Why is getting this distinction so vital?
Yeah, why should you care?
It empowers you to instantly evaluate the integrity of any claim or, any research finding you come across. When someone presents an argument, your first question should be, what are you claiming is the cause, the IV, and how did you measure the effect, the DV?
And if they can't clearly define those two things,
their argument has no foundation.
Absolutely. It moves you from just passively receiving information to actively deconstructing it.
And building on that power of deconstruction, here's a final provocative thought for you to explore on your own.
Ooh, I like this.
We know that good research requires us to correctly identify the cause and the effect. But in the real world, a lot of variables are related without one actually causing the other.
Right. Correlation isn't causation.
Exactly. So think about that example of higher education and higher income. While education often leads to higher income, there could be other confounding variables, things like family wealth or ambition or just inherent talent that might cause both education and income to be high.
So this raises a really important question. If you correctly identify an IV and a DV, but they're both actually being driven by some third unmeasured factor, how can you ensure your study is truly measuring causation?
And not just correlation.
How do you know?
That gap between correlation and causation is, it's the biggest challenge in any deep dive into data.
A great challenge to leave you with. Thank you so much for joining us for this deep dive into the absolute fundamentals of research structure.
My pleasure.
We really appreciate you bringing your sources.
Thanks for listening. If you found value in today's episode, please subscribe and leave us a review. It helps more people find the show. See you in the next one.
Hey, yo! Haven't you checked out our new book yet? Link in description.
CTS.